This is a question from CSIR NET 2023. F from R to R real valued function be a differentiable function such that f and its derivative f dash have no common zeros in 0 to 1 closed interval. Which one of the following statement is true? F never vanishes in 0 1, f has at most finitely many zeros, f has infinitely many zeros, f1 by 2 is 0. So let us consider an example, simple example. Consider fx is equal to x. This is a differentiable function, okay, and f dash x is equal to 1. So f and f dash has no common zeros because f dash fx is 0 at x is equal to 0, but f dash x has no zeros. So f never vanishes in 0 1. This is a wrong statement. This cannot be possible because we have this example. Let's just consider fourth. F1 by 2. F1 by 2 has to be 0. If this is no, f1 by 2 is not 0 here. So this is also not true. Now we are left with two options. F has at most finitely many zeros and f has infinitely many zeros in 0 1. So let us assume there exists f such that f and f dash has no common zero. Okay. And also assume that f has infinite zeros in 0 1. What we are doing, we are considering this part. Okay, we are trying to consider this part. We assume that there are infinitely many zeros. So by Bolzano-Vitre's theorem, what we will get, there exists a sequence. Okay, let us use some notation first. Let ZF be the collection of all zeros of F. Then cardinality of ZF is infinity, as we have assumed that it has infinite zeros. Okay, since ZF is infinite set, so by Bolzano-Vitre's theorem, there exists a sequence, and also ZF is a subset of 0 1 bounded set. So we is an infinite set and a bounded set. So we can apply Bolzano-Vitre's theorem, which says that so there exists a sequence xn such that xn converges to x. Xn in where xn belongs to set of all zeros of f. Now since f is continuous, as f is differentiable, this x must belongs to 0 to 1, as 0 to 1 is a compact set, so every limit point exists in this. There is no doubt in that. Since f is continuous, so we have fxn must converge to fx. The sequence of xn must converge to fx. Now these are all zeros, as xn belongs to zf, so fxn must be 0. So this implies fx is equal to 0. This implies that x must be also a 0 of f. Okay, now we will show that our aim is that now we will show that f dash x is also 0. So x will be a common 0 of both, which is a contradiction. So we will show that there is a contradiction. Okay. Okay, right. So what is f dash x? F dash x is defined as limit alpha tends to x, f alpha minus fx by alpha minus x. by sequential criteria of limit. This limit exists because f is differentiable at x. Limit f dash x is equal to limit n tends to infinity f xn minus fx by xn minus x, where we know from previous that this xn converges to, let me use a different color, we know that these xn converges to x, so we can use the sequential criteria. So this is the limit n tends to infinity fxn minus fx xn by x. Now note that fxn is equal to 0, fx is 0 because xn belongs to the 0 of set of all zeros of f, and x belongs to set of all zeros of f. So what is this? This is all are 0. This is whole will be 0. So thus f dash x is equal to 0. So what we have done, we have find out that we have assumed that f f has infinite zeros and f and f dash has no common zero, but we on a contrary we have find that f x is equal to 0 and f dash x is equal to 0. They have a common 0, which is a contradiction. So our assumption that f has infinite zeros in 0 is wrong. So this can also not be true. This is the true option. F has at most finitely many zeros.